next is false positive rate. Okay, what is this? It is trying to see from all of the actual negatives, how much, okay, or how many is it that we keep on predicting it to be positive. Okay, so we keep on predicting it to be to be positive, which is actually incorrect, out of all of the actual negatives. Because when it's false positive, it means that it is actually negative. Okay, so how many is it out of all of these actual negatives we keep on predicting, mispredicting it to be positive? That is the portion of it. Okay, all right. The next one is specificity. Okay, specificity is the opposite of true positive rate or sensitivity, because with specificity, okay, we want to know the portion of all of the actual negatives. How many is it that we correctly predict it to be negative, right? Remember, sensitivity is out of all of the actual positives. What is the portion, or how many is it that we correctly predicted it to be positive? Okay, this is like good decisions. Okay, but with specificity, it is the negatives that we are interested in this case. In sensitivity, we are interested in knowing about the positives that we have correctly predicted. Okay. Specificity can also be calculated by doing 1 minus the false positive rate. Okay, it is the complement of it. Next is precision. Okay, so with precision, we want to know out of all of the prediction of positives that we have made, okay, how many is it that we actually did predict it to be correctly positive. Okay, so the predicted yes, okay, will come from, okay, all of our prediction. Okay, even though our prediction can also be incorrect, like in false positive here, in the case of false positive. So this is our perception, okay, from all of our perception of what is positive, how many is it is actually positive. Okay, so we want to know the precision, okay, of our prediction. And the final one is prevalence, right? So prevalence is interested to know, to answer the question of how often does the yes condition actually occur in our sample. So how many is it, okay, that the positives occur in our sample? So it is the denominator is the total, which is 165 of all of the training set. So why is there so many of these measurements? This is considered, if it's in manufacturing, for example, manufacturing of a car, let's say. So once you've built a car, you want to be able to do a stress test on it. You want to be able to see whether the fuel is really saving. So you try to drive around with a full tank. You want to see if it is the airbags will work. So you crash the car and see how much impact that a car can actually take on that model. Okay, the car of that model. So these measurements are the same. Okay, but it is a stress test in a way. Okay, but for the model that we have chosen, the model is usually, the algorithm is always the same. I mean, if it's a decision tree or a naive Bayes, it's always going to be that. What differs is the data set that we input into this algorithm, that we teach or we train the algorithm. So different data sets have different characteristics. Therefore, the output, okay, is going to be different also depending on the data set. Therefore, when we do all of these measurements, we are doing a so-called stress test, quote unquote, okay, on the model based on the data set that we have. So when there's any changes in the data set, for example, there are new points coming in, there has been some changes in the policy, for example, then your training set has to change to reflect the population. Okay, and therefore you need to rerun or retrain your model. Therefore, when you do that, you need to also test it. You need to measure its performance all over again, which is all of these stress tests, because it may differ due to the change in the training set of the actual population. So let's say if we have two models, okay, or let's say two algorithms, right? Algorithm A and algorithm B. In the case where we have a balanced population, where we have the positive classes 50% and the negative classes to also be 50%. So it's 50-50, a balanced population. Okay. Here we can see that algorithm A is better, okay, at predicting positive classes, because you see here that it is able to predict all of the positive classes, all the churners, okay? The possible churners. Whereas algorithm B is good at predicting all of the negatives, okay, which are all the people who are not going to churn. Okay, but algorithm A is not that good at predicting true negatives or negatives. It keeps on classifying or predicting that some of these loyal customers are going to churn. Okay, and algorithm B is keep on, okay, mispredicting that some people who are loyal, okay, who are going to churn are actually loyal. Okay, so depending on the domain of churning, okay, in the case of churn here, which one is more damaging, which one is more costly, okay, in which area that is more costly. So the decision here is to decide whether we're going to take or deploy algorithm A or algorithm B. Which one is it that we are that is giving us better performance? If in the case that we are able to differentiate the cost of errors, then it is easy for us to decide algorithm A or algorithm B is more suited or have better performance. We can just simply choose the algorithm that is able to predict more of what we are interested in, okay, and less of the errors that we find damaging. So let's say if we find false negatives, okay, is more damaging, right? In this case, false negative would be people who are loyal, okay, who are churners but considered or predicted as loyal, so they are false negatives. Yes, okay, so they are considered as loyals. So if, let's say, that is more damaging, therefore we can actually choose the algorithm that produces less of false negative. Okay, so therefore Okay, we can, so therefore we can choose algorithm A, okay, algorithm A instead of algorithm B, because algorithm B keep on having a false negative here, because they are people who are going to churn, but we predict them to be loyals. Okay, so this is the part of the error. So we can clearly or safely choose algorithm A. Next, if let's say there is no difference in the cost of the errors, whether we predict it to be false negative or false positive, you know, the consequence or the cost damaging is just the same. Therefore, in that situation, we can simply choose either algorithm A or algorithm B. It wouldn't matter. But if and only if we are having a balanced population. Okay, so if let's say there is a difference in the cost of having having false positive or false negative, and it just so happened that our population is imbalanced. Okay, we have an imbalanced data set where we have a lot more negative examples, okay, or negative labels compared to the positive. In reality, this is usually the case. Okay, it's usually the case because the positives are usually rare, remember, okay, and the negatives are usually in abundance. So when we have a situation like this, okay, when the class proportion changes, therefore the relative performance changes greatly, because you can see here that it appears that algorithm B is having is making very little incorrect predictions, okay, very little compared to algorithm A, whereas algorithm B just now was doing a very grave error, okay, misprediction, because what it is doing is that it is predicting churners to be loyal. So you're going to have churners that keep on appearing in your customer base or your customer database, and it appears like as if even though you have data analytics, you have machine learning algorithms, but you keep on having this problem over and over again of churners popping up. So you don't want to have that, right? So in this situation of imbalance class or imbalance data set, if we're using accuracy, the performance is going to be kind of like, we can say, misguided, okay, or misinterpreted, because we will think that algorithm B is better than algorithm A. Yeah,